Hello, everyone. My name is Elliot. I'm from the ANFF Queensland node. So today, I would like to talk about a topic as photolithography. This is an area that I'm very passionate about. So I've been working in this area for probably close to 10 years. And I've also worked with Intel for 3 years on developing a new approach to address the 22 nanometer node fabrication. So hopefully today, I'll be able to show you, give you an overview of the what is currently used in the photolithography these days in the industry, and also cover some of the basics. And this morning, Doug Mayer has covered the photo masks and why they are important, and then also he covered some of the processes for photolithography. So what I would do is actually go into slightly deeper into the chemistry or a little bit of physics of photoresist, why they work, why we need them, and how do we choose them, how do we utilize them for different exposures. And in the end, I'll cover some of the practical process flows that we do in our clean room, and also some of the important practical considerations that you might need to understand before you start your projects. Okay, so what is lithography? Actually, this is a 200-year-old technique. Was invented by a German named Sennenfelder in 1796. And so he named this technique after a Greek term of lithos, means stone, and graphene means write. I'm not a Greek, so I don't know whether this is the correct pronunciation. But basically what it means is that writing into a stone. And this is what they do 200 years ago to make prints of newspaper and posters. So what they do with the lithography process back then was they actually created a wax pattern, and from a piece of paper, transfer that wax pattern onto a limestone and use the acid to etch into the limestone. So literally, this is a way to mass produce hundreds and thousands of poster flyers back then. So here you can see an old picture. That's what they do with lithography. These days, when we talk about lithography, we are mostly talking about pattern transfer techniques. Same as writing into stones, where our stones are now a silicon wafer, and our graphing or write process is a process that we use photon or electron beam or charged particles or X-rays. There are many ways to do this type of lithography, so which I will touch base on some of these techniques, but our main focus today is photolithography, which is the mainstream lithography processes used by the industry. So what I will do is pass this silicon wafer, if you haven't seen one before, around. So these are the stones we'll be trying to pattern in the photolithography process in recent days. Okay, so why we need lithography? Doug covered a lot of prospects about the design, the project. So apparently, lithography is a really important process. Probably is the cornerstone for most of the microfabrication processes you see these days. So we all like technologies. I would say lithography is the main driving factor for technology in this century. Things like computer chips, mobile phones, diagnostic devices, even the airbags, all of these technological advances are actually improved and gets better and better from day to day with the advances in lithography. Next. So you will not be able to complete a lithography talk without covering the Moore's law. Probably most of you have heard of the Moore's law, which is basically the 40 years of scaling of transistor feature sizes back into the 70s. So at the very early stage, we were only able to pack about, say, 1,000 transistors on a single chip. And nowadays, as we are close to the new era, we are looking at into more than 1 billion, 2 billion, eventually into 10 billion transistors on a single chip. And why we are doing this? Because scaling makes things better. And I'll just be touching on why we are scaling this in a second. So when I started my research in my PhD days, we were into about, I guess, the 1 billion, sorry, maybe 50 million transistors. And at that time, I remember the process was 0.13 micrometer. And the industry has been pushed very hard to get more and more transistors in on the same chip every day. And basically, this guy, Goldenmore, basically observed the scaling and how this is happening based on 2 or 3 dots at the beginning of the map. And he was able to come up with this amazing prediction of how the transistor will be scaling in the future. And it is accurate even till today, but they were having a few different versions nowadays because there are different considerations how the chips are made. A professor called Robert Denner also observed at the very beginning of the transistor scaling, and he has come up with these MOSFET scaling rules, basically saying that if you can scale your device dimensions down to a lambda, everything gets better. So if you keep scaling down, everything is better. There's no trade-offs. For example, if you remain your doping concentration as lambda scale, your dimension is 1 over lambda, your voltage required to switch the transistor is also 1 lambda lower. Your current is lower, your capacitance lower, your delays is less. So you can switch the transistor faster and faster, means you can have faster and faster CPUs. And you're going to consume less transistor power to switch while the power density remains the same, which is really true. And that was considered a golden era of transistor scaling until about 2005, when things start to fail, mainly because the voltage required to turn the transistor on and off is getting really close to the noise level you get at room temperature, which is about 25 millivolt. So in order to compensate that error, your voltage is currently not scaling down at the same rate as it should with your lateral dimensions. And because the voltage is not scaling down at the same rate, your current is not scaling down at the same rate, your capacitance, your delay time is not scaling down at the same rate. So since 2005 onwards, you actually don't get any improvement in transistor performance in terms of the clock speed. So today, most of the new CPUs you get, the reason why we are still scaling down in the industry is because we are aftering more functionality. So maximum number of chips will increase your calculation capacity. Also, I guess the biggest driving force is the dollar sign, which is always cheaper to integrate more transistors on the same chip as to integrate less and put more chips together. So they are pretty much driven by the economics these days, and that's why we're still scaling down. And very soon, it will be more and more difficult to scale down because of the fundamental limits of the optics being faced these days. Okay, so when we talk about microfabrication, most of the time we talk about what we do here, and this is pretty much like we're making devices into the microns range using standard photolithography. So as I mentioned before, lithography is probably the cornerstone, the foundation of microfabrication. It serves as two purposes. So you can either use it as a physical patterning method on a substrate. For example, you can mold your resist feature, like how you do it in PDMS soft lithography. Or you can use it as a temporary mask. And the term temporary is very important because after you finish your lithography, after you etch and deposit your materials, you actually wanted to remove these materials so it doesn't leave any trace behind. Then you can continue on with your next lithography process. So when we talk about CPUs, now we are into hundreds of steps of lithography plus deposition, etching. So pretty much every 1 or 2 or 3 steps, you will need a lithography step to mask your implementation, your deposition, your etching, and so on. So lithography are basically based on electromagnetic interaction with solid. where we use the photoresist. The photoresist is a active polymer, which we'll touch onto the base later on this topic. So the electromagnetic interaction can come from photons. Photons, if they are photons, they are photolithography. If they are electrons, they are electron beam lithography. If they are ions, they are ion beam lithography. And photolithography are usually a masked lithography. That means you need one of these photomasks to pattern your surfaces. Whereas electrons and ions are charged beam lithography. You focus the beam onto a single spot and sequentially raster through your pattern. So these are maskless lithography. And there are also alternative technologies that I will not be covering today. For example, you can use nanoimprint to transfer a physical pattern by embossing into another polymer feature. So you can do this sort of lithography as well, and there's no resolution limit. It all depends on how small you can make your master with. Also, these days, directed self-assembly are the new trend that's probably going to overtake the 193 nanometer lithography for the next generation transistors. I will not be covering that as well. And this morning, Jen also covered the reason why we need the clean room for lithography, because you don't want the dust or dirt or contaminants to affect your patterns. Think about your knob patterning things down to, say, less than 50 nanometer or even 20 nanometer. And the acceptance, if you talk to the IC industry, they will not accept any devices with more than one defect per inch square. So you will need, when you make a 12-inch wafer, and they will not be happy to have more than one or two devices that actually failed from your lithography processes. So clean room is very important. And the reason why we need to use yellow light is also because the material of photoresist is sensitive to the UV component of the white light. So a yellow light will help mitigate that problem. So this is just a lithography process in a nutshell. So basically, in order to do this very well, you need to have a good understanding of your polymer chemistry, your surface chemistry, understand your optics, and also you need to be very good at process engineering if you wanted to do something like what Intel do. But in our lab scale, we have a lot of flexibility to work on our processes. And some of the examples I will be showing you today are probably a bit of overkill for what we do in our clean room, but it's good to understand from their point of view why these are important. Okay, so you always start with spin coating a polymer resist on the surface, and following that, you will need to do a baking process to drive out the solvents in the film. And again, I'll touch on all this later. And then you do a irradiation of your UV source or your charged particles such as E-beam and electron beam. And then you need the post-exposure bake to initiate the process. Not all the resist requires a post-exposure bake, and I'll cover that later. And after you finish these processes, you actually induce a post-solubility switch of your material. So when you soak your substrate with pattern resist in a developer, some patterns will become soluble in the developer. If they are positive resist, if they are negative resist, they are actually insoluble. And once you have this template, which is a temporary mask, you can use this mask for etching and deposition. And then you repeat the cycle again over and over and over again until you finish the overall device. Okay, so let's look at the basics for lithography. They are probably classified as 4 main ingredients. The first ingredient I'll be covering is the energy source. And I will not go much deeper into just show you what you can do with different energy sources. And of course, the focus today is still photolithography, which means photon-based system. Okay, so this is the different type of scaling chart than the Morse chart. But however, we are actually looking at the feature sizes versus year. And all these dots represent a different technology node. And all these bands here represents the different wavelengths that they use in the industry to drive things down. So in most of the clean room in universities, you're looking at the H-line, G-line, and I-line exposure tools, which represent 405, 436, and 365 nanometer wavelengths. Then once you move on from that, you actually go into the deep UV range using excimer lasers such as krypton fluoride or argon fluoride, representing 248 and 193 nanometer lasers. And that is capable to pattern currently down to about 10 nanometers. And then in the end, you will be scaling down to extreme UV range, which your wavelength is just 13.5 nanometers. So most of the transistor scaling can be approximated using this formula, where R is the resolution, and there's a K1 and K2 factors. So if you look at the K1 factor, this is the resolution enhancement technology available to you at each node. And they probably kept around 0.25. So if you want to make smaller features, what you can do is you can easily reduce the wavelengths, you can increase the numerical aperture, or you can reduce the K1 factor. But K1 factor is pretty much fixed these days because this depends a lot on your optics, on your processes, and on your equipment. So as you can see that if you are scaling using the H to I-line region, you have a resolution approximated to about half of the lambda. So saying that in the industry, you will be able to scale down to just under 200 nanometers with your 365 nanometer wavelengths. Things changed a lot since the introduction of 248 nanometer onwards. So, and you can see that it's even, how is this even possible to make 10 nanometer these days using the 193 nanometer lithography? It doesn't make any sense to you. But the way the industry is doing is that they would use what they have on hand and try to improve from it. And they have been doing this over and over again. So resolution limit for 193 nanometer exposure actually kept about 45 nanometer. So in order to beat the resolution, the scientists have been coming up with this newer and newer technology, such as the introduction of immersion technique that increases the N factor of the numerical aperture to increase the whole NA, which resulted into reduction of R. So they were able to do that to push from 45 nanometer to 32 nanometer, and that's a really hard stretch. And beyond 32 nanometer down to about 10 nanometer, they use a process called double patterning. I will not go much deeper into double patterning, but basically what it does is use your existing patterns and try to coat the sidewalls, and then do another exposure, coat the sidewalls, etch, and repeat after once and twice and 3 times. So each time you scale from 32 to 22, 22 to 15, 15 to 10, you add 25 extra steps in your lithography process. And that costs a lot of money for them to push. And this is all because the next one, the UV lithography system technology, is not mature. So nobody knows what's going to happen by 2020, whether EUV will work. But in order to keep scaling down following the Mohs chart where things are better and cheaper, they just have to keep doing the double patterning in the meantime. Okay, so the chart I showed you before are basically photon sources, so photolithography. There are, of course, other ways to do this using, for example, charge beam, such as electron beam lithography, where you use a high energy electron to hit your substrate or with photoresist on top. And this energy, these electrons usually have energy from 10 kilovolt to 100 kilovolt. So they will start to scatter your material, generating secondary electron. And the secondary electrons, about 2 to 5 e-fold, are actually responsible for your exposure of your resist. Alternatively, focused ion beam lithography has been used. This is by basically sputtering atom with another ion in high vacuum. So the state-of-the-art system are the helium system, but the mainstream system are gallium. The biggest advantage of the helium system is you don't have any contamination, which Whereas if you use gallium, you actually dope gallium all over your feature surfaces. So both of these two charge beam lithography tools doesn't require a mask. Instead, you use the computer to generate your design and raster the beam according to your design. And another case is the X-ray lithography, or also usually called as LIGA. This is in German term of lithography, something I cannot pronounce them. And LIGA systems are, in theory, has the best resolution because you use the X-ray system, which has really small wavelengths of light. But in order to mask, so LIGA is a photolithography process, so you need a mask. But in order to make that mask, to mask an X-ray, you need a very dense material, which is usually made from gold. And you need a very thick and dense material. That means the cost of your mask is tremendous. And also, you're limited by the resolution of how you can generate your mask. So LIGA process are only used for very, very high aspect ratio resist, such into hundreds microns of region. So you can do that in one shot with LIGA, and you're going to get almost perpendicular side walls. Because this is just how X-ray can penetrate through the material. And Doug also covered that two-photon lithography, which is also a new disruptive lithography techniques that can create 3D structures in a resist film. Okay, so the second ingredient for lithography is the photoresist. So it's actually one of the most important properties that you need to understand. You need to understand these properties very well in order to get good lithography done. So photoresist, if we look at the words photo and resist, we can actually break it down and understand how this works. So photo means that someone can transfer the image, i.e. can be patterned. So you can take a photo, transfer it to something. And resist, so means that this polymer, not only you need to be able to take a photo, but also you need to be able to resist something, such as the development liquid, and you need to be able also to resist the implementation of your ions or etching and development. So photoresists are really important because you need to have certain stability in order to carry out all these processes sequentially. Another important property for photoresists are you need to also be able to remove it when the process is finished. So that, like, think as a painter's tape. After you paint something, you remove the tape, right? So you don't leave any traces. So it's not going to interfere with your subsequent processes. So removal is actually a very important feature for resist. But however, this is not an easy task sometimes. So you actually have to use different approaches to remove that polymer layer, especially if they are cross-linked polymers. So photoresist comes into two types. Positive or negative. There's actually a third one called the dual-tone resist. You can use it as both positive and negative, but I'm not going to touch on that in this talk. So think about you have a photo mask. You have your positive film and your negative film on a silicon. When you shine the UV light through the mask onto your resist, a chemical reaction starts to happen. So for positive resist, they are usually based on one of these three mechanisms. DNQ Norfolite, which I'll touch on later, a chemical amplified process, or transitioning process, which means that all the polymer chains getting cut. And so that allows all of these three type of positive resists have the same property to increase the solubility in a developer after UV radiation. In terms of negative resist, you're doing the opposite. You start with small chains of polymers. You actually after UV radiation, you start to initiate a process in the end that it's going to increase your molecular weight of the product, and which makes it insoluble in a developer. So again, this is all about solubility switch. Now let's look at what makes photoresist. So photoresist, I can say probably 90% of the photoresist have 2 or 3 of these ingredients. So to make a photoresist, first of all, you need a metric resin, which is a polymer backbone that need to have certain etch resistance required by the industry or your process. You need to have certain temperature stability, so it will be able to survive your deposition or etching processes. And that's the metric resin. And a lot of the resists also have a sensitizer, which is actually a photoactive compound. So this compound is very important because when you shine the UV light to this polymer resin, sensitizer is the one that does the work at the beginning. And then the third one is the organic solvent. Probably most of the polymer resists are dissolving organic solvent, so you can actually spin coat on your wafer. And the choice of solvent, of course, based on whether you can these resist mixtures are soluble in the solvent or not, and how well they can coat your wafer. So in the early days, I'm referring to back to the 60s. That's when photoresists were invented. At the very beginning, negative resist was invented by Kodak. So the way how they work is that you have your polymer blend of resin and sensitizer, and then upon UV radiation, you start to activate the sensitizer. It's gonna start to initiate the resins to cross-link to each other, and after you bake the temperature, you basically speed up the processes. You're gonna have diffusion of the cross-linked or the product. So that's why most of the negative resist process, you need to have a resist. You need to have a post-baking process because you wanted to initialize you wanted to diffuse the or propagate the cross-linking of your polymer along the direction. So you can also see that's also why most of the negative resists have very straight sidewalls, because you'll be baking this on a hot plate, so there's a temperature gradient from the bottom and the top, so they tend to go vertically. And after you develop the resist, these areas, the molecular weight has now increased a lot. They are not soluble anymore in the developer, so that makes them negative. These resists are very hard to remove. Some of the resists we actually cannot remove them. So a classic example is the resist called HSQ. It actually is a silicon-based photoresist, and it turns into oxide. So another name for HSQ is flowable oxide. So after you cross-link it, it turns into oxide. So the only way to remove it is with strong acid or strong base, but very hard to remove because if you use strong acid or strong base, you start to attack your other materials on your wafer. So that's not preferred. And also, if you are using an organic solvent to develop your negative resist, which is probably most of the cases, you could get a swelling effect. That means your resolution could be limited. So the industry really quickly ditched negative resist in about 10 years' time. So these days, if you wanted to work with the industry, with the semiconductor industry on a photoresist project, if you bring up the name negative resist, they would definitely say, no, we don't want this. And if you bring out the name about a solvent developer, they will also say, no, not possible. So they are only happy with positive resist and aqueous development. Okay, so let's look at the next positive resist breed. As I mentioned before, we have the DNQ Norfolite, we have the chemical amplified, we have the transition. So I'm not a chemist myself, so I will try my best to interpret this one. So in a DNQ Norfolite resin, these were invented in the 70s, and these are the resists that we still use in our clean room every day. Resists such as the popular AZ1500, 9200s are all made of DNQ Norfolite resist. So you have, again, three components. You have your backbone polymer resin to allow you to have enough etch resistance and temperature stability. You have your DNQ sensitizer. This DNQ stands for diazonephenquinone, I think. So what this DNQ will do when you irradiate with UV is that it's going to turn into a carboxylic acid component, which allows it to be highly soluble in a base solution. But if you look at the chemical structure of the D and Q, and you look at the end product, there's a hydrogen in there. So where's the hydrogen coming from? It comes from the water, but you are not using any water during your exposure process. So the water actually comes from the moisture or humidity in your clean room. So if your clean room has no humidity or humidity is too low, the D&Q process will not work. So you need to have about 40 to 60% of humidity in your clean room in order to trigger the solubility switch in a D&Q no-flake process. So once you trigger the D&Q process, it turns the resin soluble. So the D&Q sensitizer actually inhibits inside the polymer resin. So the more D&Q you have, the more soluble it becomes. So that's one type of resist, and we need we need water. This is usually called the rehydration steps. So you'll find out after you expose your resist in our clean room, if you're using the AZ resist, you need a couple of minutes for the water and to take place to help with the solubility switch. The next one is called the chemical amplifier resist, and this was invented, I think, in the 80s. And these resists are the driving force of our scaling all the way down from 0.5 micron to 10 nanometer currently. I think the three scientists who invented chemical amplifier resist actually won a Nobel Prize for their achievement. So short name as CAR, okay, chemical amplified. It's used from I-line to EUV. So with the chemical amplifier resist, you have your sensitizer or photoacid generator. So if you look at the processes, you start with your photoresist, you expose with the UV light, you're gonna start generating acid. Okay, so this acid generation were actually coming from the PEG process that interfere with the interact with the UV, generates a very strong acid plus the other components. So this acid will then attack this polymer resin, which is the backbone. And the way we describe this attack is called a deprotect. So when the acid from here deprotects the resin, you ended up with this very soluble phenol polymer that can be developed into your photoresist. So, but in order to trigger this solubility switch, you need both acid and heat. So chemical amplifier resists tend to diffuse through your resist film, also the sideways as well. Because think about this deprotection. If you have acid deprotect this one, it's going to generate another acid. Another acid will look for another site to attack and deprotect your polymer resin. So one of these PEG switch can actually initiate quite a few of these polymer deprotect mechanism. That's why they are so popular in the IC industry, because the sensitivity or the dose required to pattern this resist is significantly lower than the D&Q process. So once you have the phenol, you can develop it, and that's just showing that you get much more acid after you post-bake it. As soon as you stop the heat, the post-bake or the acid diffusion will stop. Also, you're likely to develop this resist in a base solution, because not only you wanted to have a controlled environment so you can actually neutralize the acid as you generate the acid, and that's why this is a really controlled process. The third type of photoresist is a transition resist. So these are usually primarily used for deep UV or e-beam lithography. So think about your polymer film as a PMMA, polymethyl acrylate in this case. If you shine a deep UV or EBO light, electron beam to the resist, it's going to start cutting these polymer chains. These polymer chains are very easily cut with about 2 to 5 electron volt of energy. It will turn this big polymer into smaller fragments and make them soluble. And you can see this is a simulation diagram of the depth of the film, and you also could generate something like similar to this because the intensity is higher on top, and then the intensity will gradually reduce. This is in case of the deep UV process. So once you develop, you're left behind with area that has not been sectioned. The beauty with the transition process is the sidewall and the resolution is very, very high because you don't have the SU diffusion problem. Also, you don't even need a post-exposure bake process. So if we look at with all the resists, you're going to have this trade-off called the RLS, means resolution versus dose, sensitivity-wise, or versus roughness. So if you have a resist which are very sensitive, you have to sacrifice your resolution and the roughness. So you might get something like, instead of a nice smooth line, you might start to see some edge effects, which can then somehow be transferred onto your device, and it can deteriorate your performance of the device as well. And so to make the perfect polymer blend, actually the perfect doesn't exist. So you have to sacrifice something. So usually they work around an area where either resolution is important or roughness is important. But in the industry, they mostly care about the sensitivity as well because they wanted to be able to push, in these days, 200 wafers per hour for lithography process. If you do this in a clean room, probably you can have 1 wafer per day, 2 wafers per day. That's OK. But industry, they will be producing 200 of these per hour. So they need very, very high sensitive resist. Which brings to another topic, important property of resist, the contrast curve. So each resist has a sensitivity factor. So this is usually referred to as the ratio between the resist that's fully intact to the resist fully developed. So if you look at this chart, it's basically a plot of film thickness remaining versus those. So here we have 3 resists, each one with a different plot. The red one, of course, has a higher sensitivity. The blue one has the medium sensitivity. The green one has the worst sensitivity. But increasing in sensitivity actually doesn't really mean that it's going to be the best resist you choose because you still have the RLS trade-offs to think about. Another term always used in lithography talks is you have both contrast and sensitivity. Okay, so first sensitivity is the dose required to clear your resist film after exposure. And both positive and negative resist will have this curve, but they're going to be looking totally opposite. I'll show you a chart later. With contrast, now you're looking at how fast you can totally dissolute the resist from 100% of film thickness to 0% of film thickness. So resist, in this case, with the red one has the highest contrast, and the green one has the lowest contrast. Typically speaking, the contrast factor in photoresist are about 1 to 2. In the high-end industry, in E-beam, for example, the contrast is usually 6 to 7. So the higher the contrast, the better the resolution you can actually achieve, because you wanted to be able to control the exposure precisely, so you have much broader dose window for you to optimize your process. So by looking at both positive and negative resist together, you can see the contrast curve looks just totally opposite. Ideally, the best resist, you should have infinite contrast, means that as soon as you reach the dose, the film is totally removed. And it should have the same dose for clearing and same dose for remaining films, but it doesn't really exist. Okay, so most of the sensitivity we work in our eyeline resist in the clean room are about 100 millijoule in this case. Okay, Doug this morning has already covered about the masks or photo mask. So I'm just going to really quickly touch on again, the differences between mask and maskless. So this is usually the split point for photolithography, whether you go for, if you want something really high resolution, maybe you need to go for direct light lithography. That is usually called the maskless lithography because you don't have a photomask anymore. But what you have is a lot of the computer calculation. You have a lot of beam movement. So this process is usually a lot slower because with the photolithography, UV or photon-based system, you can expose all the area at once. So you can achieve 200 wafers per hour. The direct light lithography, you're looking at a wafer per month, for example. It's just the scale difference. But with EBL, for example, it has been demonstrated to give you 2.5 nanometer of resolution. So the system that UQ recently bought has, upon installation, has achieved 7.5 nanometer resolution in the first shot. So this is a really good system that UQ is getting. So again, photolithography is the one that we're going to cover today. Direct light is something that's going to be planned for later this year. But the laser mask writer that was covered this morning was also a direct light lithography. But we don't usually use it for our microfabrication, apart from making masks in the clean room. Because you have to make, each time you make these wafers, it takes about 3 hours. So if you need to make 10 wafers, you need 30 hours. Whereas you can just expose this one for 3 hours, and then you can produce each wafer in a minute or 2 minutes. Okay, the next basics for photolithography is the exposure mode. So again, there are 3 types: contact printing, proximity printing, and projection printing. So contact printing means that you'll be bringing the mask in close contact with your photoresist and apply a force so that you actually get a very good transfer of your pattern onto your wafer. So what you have on the pattern, on the mask, is what you get on the wafer, where the resolution is roughly described by square root of D, means D is the thickness of your resist and the wavelength of your light. So if your resist is thicker, your resolution is lower. And in proximity printing, you have now an air gap between the mask and your resist. And why do you do this? Because think about that, you'll be using this same mask to print 20, 30 wafers. You probably have to clean the photo mask every 1, 2, or 3 rounds. And by having an air gap, you will not need to do that because your mask is not touching your photoresist. So it becomes a more user-friendly process if you don't really care a lot about the resolution, because now your resolution is limited by D plus G times lambda with a square root on top. And if you look at what industry is using, they tend to use projection printing, means that your mask, or called the reticle, is inside your lens. So the beauty with this system is that you can usually achieve 4 to 5 times pattern reduction. So in order to make a 20 nanometer features, all you need to do is make a 100 nanometer mask, which is a lot easier, a lot cheaper to make. If you wanted to get the same thing in contact mode, either you have to use X-ray lithography, and then your cost for making that mask is extremely high. What I forgot to cover is that your resolution actually depends on the wavelength of light based on the diffraction limit of your light. So if you use, if you need to achieve 20 nanometer using contact lithography, probably the only method is either extreme UV lithography or the X-ray lithography system. So with projection printing, you have the resolution with the scaling factor of K lambda over NA, which we covered earlier. However, you also have the depth of focus, which is known as K2 lambda over NA. And K2 is about 0.5 these days. So if your depth of focus is too low, that means you will not be able to transfer the pattern into your resist film successfully. That's why these days, in our lab scale, we can use this sort of contact printing with a resist thickness of about 1 micron all the way to 100 micron. However, in the industry these days, because you're only making 20 nanometer features, your resist film are now less than 50 nanometer routinely, and some resist film are now just under 20 nanometers. So here is just the transfer, the light intensity at the resist surface from the mask to show you what sort of light profile you can get at at this interface. So with the contact lithography, you actually lose nothing. You get about nice square wave. In our lithography system, you can pull off about 500 nanometer. Depends on the thickness of resist you use and the type of mask, of course. If you use projection, you're going to have this ugly tailing, which is going to limit your resolution to about 20. Oh, sorry, if you use proximity, sorry, you're going to have this ugly tailing effect, which is going to limit your resolution to about 20 micrometer in an I-line process. If you use projection, because of the reduction, you can actually pull out a 40 nanometer CPU design these days with 193 nanometer immersion lithography plus double patterning. It's very complicated. And if you think about the type of optics required to make this sort of projection, I'll just show you a picture of a scanner from ASML. You can see that it's actually a very complicated piece of electronic optics. So the lens is probably as tall as a human. And this is the old technology, by the way. This is the 193 scanner. If you look at the current EUV scanners, you can't use the through transmission. Everything needs to be reflective. That's why the systems are so expensive to make and also very hard to maintain. Next, let's look at some of the instrumentations required for photolithography. So this can be as easy as a UV flood lamp or UV LED light or even a sunlight. You can induce this solubility switch. You can also go as complicated to a synchrotron radiation where the light gas system or the X-ray lithography are performed. The most common ones in microfabrication in a university environment are mask liner, a stepper, which is basically a projection system, but a much cheaper one than the traditional 193 nanometer scanner. You can also use electron beam lithography and focused ion beam lithography. So also you will also need some instrumentation to control the coating, which is usually done in a spin coater. You need some way to control the baking process. You need to have a way to develop these resist materials afterwards. So a standard tool for master liner comes in around $500,000. And if you look at the 193 scanner, they are about $20 million each. So if you wanted to basically ask someone to do this sort of 193 lithography for you, it's almost mission impossible, because when you talk to the industry, they will want you to make millions of your device. Otherwise, they have to shut down their machine. They lose thousands of wafers each time. And the state-of-art EUV scanner costs more than $200 million each, but you can achieve less than 22 nanometer resolution. And the funny thing is that this single system is about the same cost as a synchrotron. So you can think about in an Intel fab or Samsung, they will have probably 10 of these. So that means that the systems installed in the semiconductor industry is incredibly expensive. Then when we look at the focus charge beam, we have the electron beam lithography. They're coming about $5 million, and the heating ion beam $1 to $2 million. So we are planning for another workshop to cover nanolithography in the future. So let's just quickly go through the detailed process flow. First, to do a lithography, we need to clean the surface. So there's many ways to clean the surface. You can use a solvent cleaning, or more aggressively, you can use a piranha cleaning. A piranha solutions consists of sulfuric acid and hydrogen peroxide. It's very high temperature. It's actually pretty dangerous, but it will remove all the organics and metals on the surface. And alternatively, you can carry out a plasma process, which uses oxygen plasma. And Caillou will cover that later. And after you clean your wafer, you actually need to prime it. So to prime it, you need some sort of a vapor source, such as HMDS, or you can use the titanium primer to coat the surface with titanium particles, so you can achieve the certain contact angle, which works very well for your photoresist. Then follow that, you will be spin coating your photoresist, and so by centrifuge force. So you can see that the spin curve is probably a power curve rolling off as you increase the speed. So these curves are usually pretty predictable. You just need 2 or 3 points. You can plot this curve, and you can work out the thickness you want for your resist. But practically, if you just spin coat the wafer with your resist, you're going to get this edge bead effect. So the resist tend to be a little bit thicker on the edge. So what we usually do is we use an edge bead removal process. While we are spinning the resist, we shoot a jet of solvent to clear out the edge so that you don't have this issue. Remember that now that we talked about proximity printing before, if you have an air gap, your resolution is reduced. So if you don't do a edge bead removal, you're going to get a poor performance from your actual lithography. Whereas if you remove the edge beads, you're going to get a good contact throughout the mask. So you can get a really good resolution out of it. There's many ways things can go wrong during the spin coating. You can have bubbles in your solution. You can have particles which will show as a comic pattern or a streak pattern. If you don't use the right speed, you're going to get this swirl pattern. If you use the wrong chuck, you're going to get this chuck mark. Or if you don't have enough resist on the surface, you're going to have area that are not coated. And we've seen all of this. And if you have used our clean room facility before, you probably also seen all of this as well. So it's important to eliminate any of these problems before you go to the next step of your lithography. So after you coat your resist film, you need to bake it. So by baking, you can drive off both the solvent you can drive off the solvent from the resist film, which also solidifies the film. But you cannot. It's preferable not to over-bake the resist film because you still need some of the solvent in the resist, so you can then develop it easily with your developer. If you have no solvent left, it's a really hard film, very hard for chemicals to go in and attack. So more solvent you have left behind means you're going to have higher development rate but really low resolution. And in our clean room, or in most of the clean room, we tend to use a hot plate to bake, because if you bake your polymer resist film in an oven, you're going to get this skin effect. That means that the surface of your resist get hardened first, which makes the solvent very hard to escape from the bottom. Whereas if you bake it with a hot plate, everything escapes from the bottom upwards. So it's a much easier way to control the baking process. Next, after you finish your baking, you put it in a liner, and with your wafer, with your mask. Your mask will have some sort of address alignment markers for you to align to the existing feature on the wafer, which Doug covered this morning. So here is just a diagram showing what you have on the mask and on the wafer. So this is a really bad alignment. So if you see something like that, that means everything is misaligned. So you need to have a correct alignment, which you can usually basically, if you want to do a good alignment, you need to have a good design. A good design will allow you to do this procedure much easier. So in the end, after you pattern it, you expose it, you need to post-bake it, and which is basically means putting the film back onto a hot plate. It's optional for photoresist. If you use the DNQ no-fillet resist, you don't actually need to do the baking. But if you're using the chemical amplified one, you need to control the baking very well, down to the seconds, to get a good profile. In the end, you immerse it in the developer, and you ended up having a resist fully developed. So a good lithography, if you look at the cross-section, if this is your mask, your resist profile should like this, nice and straight, with the same dimension as the mask, nice and square edges. So it's very easy to overexpose and overdevelop your resist. The sign to watch out for is that if you notice that your resist is getting smaller or thinner, and you start to get all this roughness, and your pattern is actually smaller than the design, that means you might have overexposed it or overdeveloped it. So you need to do a series of optimization until you can fix this problem. On the other hand, if you underexpose it or underdevelop it, you're going to get another profile, which you're going to have resist residue on the pattern. So here we only talk about the positive resist. So you're going to have resist residue at the bottom. You're going to have a much bigger area. So that means your process is not optimized. So I'm just going to quickly go into some of the practical consideration for photolithography. And these are very important if you wanted to design your lithography process for your goal. So you need to actually understand how to measure each of the steps using some metrology tool, such as you can characterize the resist thickness using a stylus profiler, lithometry, and reflectometry, or SEM. And to understand the critical dimension of your developed resist, you might need to use optical microscope, scanning electron microscope, and also AFM, for example. So another practical consideration is reflection. So think about that. You have a wave length of light coming into the resist film. If it happens to be just with no phase shift at the interface, you're going to get the wave bounce back. So you're going to produce a standing wave throughout your resist film. This is usually referred to as a swing curve. So depths into the resist from the surface, you're going to have this swinging effect, which represent to your reflection. So it's very important that you need to tackle your reflection to get a good lithography. So otherwise, you're going to have these fringes on the side wall of your resist. So it could come from, you can probably solve this by having a post-exposure back process, same as this slide showing you here. By post-exposure process, you can actually blur the exposure profile along the side wall, so make it nice and straight. Or you can use more advancedly anti-reflective coating, which either absorbs all the light or induce a half wavelength shift that cancels the superposition of the reflection, so that if you have this anti-reflective coating, lights will be bounced back with very little standing waves, then you wouldn't have problem like these rough edges. You also need to make a right choice of whether you want to use positive or negative resist. And with positive resist, they are generally good for wet and dry etching. They are usually done with aqueous development. For negative resist, we tend to use them only for lift-off process. They are perfect for dry etching, but they are hard to remove. So they are usually referred to the non-sacrificial dry etching mask. You can use it to mold the PDMS, and they are usually carried out in a solvent development environment, which could not be feasible for you. So another important thing to understand is what resist profile is best for you. So if you're doing wet etching, it doesn't really matter. You can use this positive resist profile. But if sidewall angle in etching is important for you, you actually want it to be nice and straight. If you wanted to do lift-off, you actually want a negative resist profile, so you can remove the metal easily. So in terms of dry etching, if you have a slanted slant angle, it's going to follow all the way down to the substrate for you, so which is not preferable sometimes. If you have a vertical sidewall, you can etch nice and easy in an isotropic etching environment. If you have an undercut, it's just going to follow an undercut. Again, may affect your device performance. For lift-off, otherwise, you will actually tend to use the negative, the undercut profile, because the metal will break from the top and the bottom of your resist feature, so make it really easy to lift off. If you use the 90-degree angle profile, you're going to end up with these loose bits or tailing, which can short the circuit. If you use the positive resist profile, it's impossible to lift off because the edge of the resist will just be fully coated. So one last important thing to understand is how to do the alignment. So as I mentioned before, a good design will make your alignment easy. So I usually suggest students or researchers to have a search window. And also it's important, so the search window will allow you to look for the alignment aligned and carry out the next process. Also, you need to have a good strategy on selecting a layer and the order. And this is just showing you that if you design something for alignment, you need to have at least space them about 50 millimeter apart for mask aligners in our clean room. Otherwise, the optics will bump into each other, and you can't align anything. And this is just an example to show you a search window. When you overlay on top of the wafer marker, you can actually use it to align rather than if you have a negative pattern, it's impossible to align this one to this one. So think about how you're going to do the alignment strategy, and also always make the gap wider to account for process variations.